Thanks, folks, for having me. Appreciate it. And I also want to apologize. In 25 minutes, it's very difficult to give a thorough history of everything that's gone on for the last 100 years and turbulence research. So I apologize if I can't touch on everything, but I decided, since the organizers asked me to sort of, or gave me the option to focus on a bit of the work we've been doing, I'm going to do a bit of that, and hopefully that in the breakouts we can bring in some of the work that I have not been able to bring forward. So about the 70s. Well, okay, sorry. So over rough surfaces, typically we have always thought of most as applying basically that it's primal mixing link theory, where eddies that are performing the transport are scaling with the height of the surface. And that produces a logarithmic law, and then we modify that with stability based on the MO functions that you see on the right. And for plane canopies, for until the 70s, it was always thought that canopy turbulence was just like that over rough surface, but that it was physically displaced vertically, and that the mean height of the momentum sink was somewhere in the canopy, but that the turbulence was really similar to that over other surfaces, except that there might be some augmentation of the fine scale eddies that are shed in the wakes of the branching elements, etc. But that, so this is how we always thought of it. And so one of the critical achievements in the early 80s was that by Mike Roback and Roger Shaw, where they realized that we need to think about the equations of motion differently in the presence of trees, and that spatial averaging is essential. And so this all came about. If you look at this, this is, if the wind's from the left to the right, that there is a peak in the pressure at the front side of the bluff body, and a minimum in the pressure on the lee side of that bluff body, and that as a result of that, the pressure is not constant around the element surfaces, and therefore spatial averaging operators don't commute. And so when you apply this to the equations of motion, there are additional terms that show up representing the canopy form drag that you see here, and equivalently for the viscous terms, because the velocity gradient is not constant across the elements, that there is a viscous drag term that shows up there as well. So that the essence of the canopy influence shows up only if you spatially average the equations. I should note that in stationary, horizontally homogeneous conditions, the balance is basically the divergence of the flux balancing these two drag terms that we typically model as a velocity squared type formulation with a direct focus. And these are basically the equations we solve in MPS directly. Okay, but that the other point they wanted to make that they brought forward is that if you're averaging your measurements at a single point, that there is no presence of the canopy drag in those equations, that you still have to spatially average for those to show up. Because of that
pressure difference, because at a single point you wouldn't notice that the pressure is different across those element surfaces. So it required a planar average for that to show up, and that John Finnegan in '85 formalized that to more of a volume average, and then Roger and John recombined that all into a final document in 2008. So if you average at this point, you see, if you average at a point, if the wind is from one direction and you're physically sitting at a single point, you are seeing something different than if the wind is coming from a different direction, depending on where you are relative to the canopy elements. And as such, another term shows up in the equations, which is called the dispersive stress divergence. The sum of these two stresses should match the horizontally averaged equivalent. What we sit and measure with a point tower is this. If these elements are randomly distributed and not organized in the way that I show here, then the dispersive stresses should be quite small. They're also quite hard to measure, but there's been a lot of that going on in wind tunnels where you actually have physical rods, and folks can look at that in more detail. But this was a crux sort of change in the thinking in canopy turbulence starting in about the 80s. So if you look at profiles of the wind or temperature above the trees, this is the top of the trees here at the bottom here. This is from Fazu and Schwertzfeger in '89. They noticed that as you approach the top of the trees from some higher point, that a particular gradient would produce a larger flux than you would expect from most. And that starts to happen at about 2 to 4 canopy heights above the trees, and this is what we call the roughness sublayer, that which is influenced by the trees. It actually extends all the way into the trees, but that the variation that it does also vary with stability. So Mike Raupak back in '96 concatenated a bunch of experiments from wind tunnels and outside canopies, etc., and showed that there's basically a similarity across all these canopy types, that we end up with something logarithmic aloft, but that it's more exponential inside the trees. Yes, there are cases that have sub-canopy jets. There are mechanisms for that to happen, but that because of the form drag induced by the canopy elements, that you see that the vertical profile of the momentum flux diminishes rapidly with height, but that it is fairly constant aloft. Another key finding was that another key thing that folks noticed was that if this is the TKE budget, that we typically assume that production balances dissipation, but that in plant canopies, you can see that the production, the shear production, happens at an elevated height above the ground surface, and that turbulence these are wind tunnel measurements from Mike Raupak and E. Brunet, that TKE is actually exported from the top of the canopy down into the canopy, and then so it's actually distributed and moves from canopy top to elsewhere. We showed in 1997 that there's actually a pressure that it's not just the TKE transported by it's not the advection of TKE necessarily, but that there can also be a pressure transport of TKE if there's a bit of buoyancy. So the point is, the balance is, that the flow is not in equilibrium with the local balance. Okay. Another unique thing, if you look at time traces, this is a half-hour time trace at some time, it's someplace three canopy heights aloft up in the inertial surface layer. You can see that these are fluctuations of U and W, so the streamline velocity and the vertical velocity that you see. There's a bias of an equally likelihood of sweeps and ejections, but really there's actually a bit of a bias towards the ejection phase. But that as you sort of look right at the top of the trees, that you see much more organization in the turbulence. There's a much more likelihood of weak ejections, but really strong sweeping motions that penetrate down into the canopy. So something is uniquely different at the top of the trees compared to in the inertial layer aloft. Folks found that if you look at time series, this is temperature under unstable conditions at 6 heights. This is the top of the trees here, but you can see that there are these ramp-like structures. So there's weak ejections that are bringing warm air upward, terminated by sweeping events of cool air being brought down into the trees. And you can see that they are actually coherent all the way through to almost near the surface. And that if you look at an average of many of these events, this was Gao et al. In '89, and flip the time and space so it looks like space, you can see that there's this microfront of temperature and that there's this weak ejection, weak rising motions bringing the warm air from the canopy up out of the trees, terminated by a strong sweeping motion, bringing this cool air down into the trees, and that this is really unique to what's happening at the top of the canopy. These guys found that these events account for about 60 to 80% of the exchange. I could say that Christoph Thomas and Thomas Foken looked at this from a wavelet perspective, and if you look at single scales, that they found that it was more like 30 to 40% of the exchange, but that clearly these were the functional mechanism by which material was exchanged between the canopy layers and aloft. So we turned to numerical modeling, and we used LES of, so we solved the equations of motion numerically. We now have, so it's really hard to figure out from tower measurements what the 3D spatial nature of these structures look like. So we decided to turn to LES. And if you go back and look at this, you can see that because there's this sweeping motion, so downward motions merging with upward motions, peaks in the pressure that you might expect associated with that. So we looked around at the top of the trees for peaks in the pressure field and concatenated. This is from 3,000 different volumes of data where we created a composite average structure. This is a vortex identification method called lambda2 in blue, where you can see that it looks more like it's a pair of head up and head down hairpins, where you can see that the sweeping motion is in red, and that the ejection motion is in yellow. These are much weaker than the sweeping events, so you don't see the head of the head up hairpin necessarily with this at this threshold, but that between the two is that scalar microfront, and so this naturally comes out of this compositing effort that you would have otherwise seen in the observations. So we think it's this pair of head up and head down hairpins that are performing the exchange, and this is very different than what you would expect in a logarithmic layer, where it's dominated by head up hairpins and mostly these ejection events between the legs of the hairpin. So clearly, the turbulence is unique. Mike Raupak correlated that with. He thought, oh, because of the velocity profile, this looks like it's a mixing layer. Mixing layers have an equal likelihood of head up and head down hairpins, so it's slightly different than what we see in the a canopy situation, but that in a mixing layer with an inflection point, that there's an additional length scale in the problem that is tied to the vorticity thickness and the gradient of the velocity across that distance. So we put forward a theory, John Finnegan, Roger Shaw, and I, that as high momentum fluid is brought down to the top of the trees, the shear at the top of the trees is enhanced, and a Kelvin-Helmholtz, in an inflection point situation like that, that the first instability to activate is a Kelvin-Helmholtz wave that is unstable in its own right, and in that shear can form Stewart vortices that are transverse, and under perturbations to that through a helical pairing instability, that these structures can be drawn together and form these head up and head down hairpins that we see in our observations. So we think this is how these structures are formed, that it happens all the time with the large scale motions bringing high momentum fluid down to the top of the trees. But the important point is that there's an additional length scale in the problem associated with this vorticity thickness at the top of the trees and how deep these vortices can penetrate down into the canopy. Now, there needs to be a symmetry breaking mechanism associated with this. So because it's logarithmic above the trees and exponential down inside the canopy, there's an additional strain on the vortices that are drawn down into the canopy through self-induction, and that is the mechanism by which the sweeps dominate over the ejections in canopy flows. So Ian Harmon put together a theory based on this additional length scale. You can see that it shows up right here, and so they modified MO, matching to an exponential layer inside the trees to augment the mixing associated with these eddies. And when applied to neutral cases that I show here, you can see across increasing canopy density from an LAI of 2. This is actually a plant area index, so it's the total of the canopy elements and the leaves. But that they can now show that for the weaker gradient, they get the larger flux. They match the measurements quite nicely, and all the way down into the canopy, they can show that this new formulation really accounts for that additional mixing associated with these canopy eddies. But they have definitely assumed a constant mixing length in this formulation. So there was some work by Wally Dupelage, who tested a bunch of roughness sublayer techniques to augment the mixing, and definitely showed that this is the method, because of the additional physics that this represents, as opposed to just a tuning algorithm. This really has shown the best mechanism, an improvement in the ability to reproduce fluxes and gradients in the presence of trees. We took the same formulation and put it in our climate model, land surface model, drove it for, I think it was 81 months across 8 different sites, driving the land surface model with observations above the trees, and saw improvement across all the fluxes, even though this is really tied to shear at the top of the trees. So, this mixing length, you could see, so we looked at this in 2016, that this vorticity thickness, these are 2 different, so at Chats, this is a field campaign we ran where we measured for a month before there were leaves on the trees and a month after the leaves are on the trees, and we showed that the vorticity thickness is definitely influenced. It's larger when there's fewer leaves on the trees, as the eddies can penetrate deeper. Botarini et al. Recently looked at this at the Atto Tower and showed that across a range of stabilities that that this length scale is affected by stability, but that it's valid, that you can show that this works across a range of stabilities. But I want to point out that there's a couple of points here that are kind of hiding, that at the broad range of stability, really stable and really unstable, where the shear is not the primary mechanism by which these eddies form, that we still don't know how to model exchange in these end member points. So this is where I bifurcate a little bit and focus on our work, where I'm going to focus on the unstable side of this, where we've been doing a lot of work lately. There's still a lot of work that needs to be done in the stable side. So to get at this, we ran some simulations with so they are full boundary layer resolving simulations at resolutions where we can still resolve the trees. We built a vertically resolved land surface model, so we actually solve leaf energy balances at every vertical grid point that is implemented at every horizontal grid point. So these are sort of living, breathing trees at every individual point that are the average of many of these trees. But we hold all the forcing constant, except that we impose a pressure gradient that drives the flow at different speeds. So all we've changed is the geostrophic wind from 20 meters a second down to 0. And there's a capping inversion at about 1 kilometer. So that sets the length scale of the large scale eddies. And so at about a height of 6 times the height of the trees, you can see that in the mix of buoyancy and shear that you see here, where shear is dominating, that you end up with these large roll-like vortices. This is vertical velocity, so narrow bands of rising motion surrounded by large regions of sinking motion that set up these large roll-like structures. And that as buoyancy becomes more and more important, you end up with Rayleigh-Benard-like cells. And the question is, how do these large boundary layer scales of motion participate in the vigorous exchange at the canopy top as the winds get weaker and weaker? Okay, so if you take it as an instant in time, in black and white, you can see a low-pass filtered slice of the vertical velocity that I just showed you. That's up at about 6 times the height of the trees. You can I put that there just so you can see what the large-scale motions are doing. And then in the colors, we look at a spatial quadrant analysis down at the top of the trees. So this is where, so we're looking at ejections in green, sweeps in blue, and for momentum, and then ejections of heat in red, and injections of and sweeps of heat. So basically cool air being brought down in the magenta. And that if you look in the shear dominated situation, you can see that that they are highly correlated. You see most of the blues and the pinks together, and most of the greens and the reds. But that as you move to free convection, that you can see that they are very separated. The regions where the exchange of heat and momentum at canopy top are happening in very distinct locations spatially, that the reds are all tied in with the regions of the upwelling motions of the large scales, and that and the magentas are all centered in the center of the downwelling motions, and that the sweeps are all on the sides of these large eddies that are impinging on the top of the trees. Okay, if you look at this statistically, I took this from Dan Lee and Heli Boussaid's ideas, where they were looking at the correlation coefficient between the momentum fluxes and the heat fluxes in this particular case, and that as you move from near neutral to free convection, that the fluxes become distinctly decorrelated with increasing instability. So this is a spatial spatial analysis of their problem. So how does exchange happen at the top of the trees? I can say that I'm not going to show it here because I don't have time, but that in the regions of high shear, at the bottom of where there's shear associated with those large scale eddies, we find those same mixing layer type eddies. But in the regions of weak shear, this is a concatenation of many many slices of data here, where we find this is temperature in the colors and the fluid motions associated with that, that we find thermal plumes that are rising out of the trees and that they are coupled with the large scale motions in ways that they're inhibited in their vertical depth as associated with the downwelling motions aloft when you look under a downdraft, but when you look under an updraft, they are rising, they are all collected up in these large scale motions and the exchange of most of the heat there. But the point is, at the canopy layer, that the length scales of these, that these extend up to about 4 times the height of the trees. This is part of why we see the roughness sublayer that is, between 2 and 4 times the height of the canopy, that there's a mix of these buoyant eddies driving exchange up to about 4 times the height of the trees. And we speculate that the horizontal scale of these is set by the absorption depth of the radiation through the canopy, that there's a length scale associated with the radiation absorption that sets the length scale of these plumes as they come out of the trees. We're using this, so clearly, in free convection, there's a mix of these 2 types of mechanisms that are contributing to the exchange. So the parameterizations that we're developing need to account for sort of a mix of both as we move forward. So some of the critical questions that remain, these are horizontal slices of, as I said, we solve for leaf temperature at every single horizontal grid point of the canopy elements. We see evidence of the large-scale structures in setting what the leaf temperatures are based on those wind fields we saw, but that also implies that the sources of heat and moisture are also tied to those large-scale structures. This has important implications for averaging times for measurements. If you're sitting at a single point, that there's actually a spatially varying source around you dependent upon what the turbulent structures are doing and their character at that time. And so I want to put forward that this is for completely horizontally homogeneous trees. This is just the influence of the large scales of the turbulence, and it results from the rapid response times of the leaves, the small thermal heat capacity of the leaves, and how rapidly they can respond to thermal forcing by the large scale eddies. And the question I ask is, if you have, large scale, if you have cloudiness over top, patchy clouds, how does that change the way the exchange happens when there's a change in the source distribution? So this is stuff that Jordi Vila's group has been looking at a little bit in a more cursory fashion, but the point is, these are important pieces of the puzzle that are not incorporated in any way in our parameterization efforts thus far. Stable conditions, as I mentioned, it's still an important thing, and just because of that thermal heat capacity, you can get very unique structures of the temperature in the mean. This is just over a 6-hour period that you get rapid cooling of the leaves at an elevated height. Soil is still warm at this time, and you get unstable mixing inside the canopy and a real stratified layer across the top of the trees. I've seen as much as 10 C across, a 2-meter distance with measurements at chats. So I mean, this under weak winds, this happens a lot. And then I also want to mention that as a result of this, these are LiDAR slices across the trees at the top of chats. And this is the non-stationarity problem that we also have yet to deal with, but I want to point out that this is the orchard here, and you can see the formation of gravity waves across the top of the trees is right there. You can see them again. But the point is, these, if these break, this changes the whole sort of paradigm of how we model things at canopy top, the exchange at canopy top in stable conditions, meaning we don't know how to do that yet. The other thing that we don't know how to do yet is we don't have a unique theory that transitions across the range of canopy densities. There's been a lot of work on single trees going on. We saw some in Charles's talk yesterday, but that there's a whole variety of canopy types that while the mean wind, we just don't have a theory that transitions completely across this broad range from single tree to organized but yet sparse, from sparse random, and then to fully tall canopies like that in the Amazon, where they're even finding at the top of the trees that there is no inertial layer above these trees. So there is a suggestion of that. So there's still a lot of work to do in that, but there's just really no theory yet to transition across these. And then I wanted to also talk about the influence of trees on hills, just briefly. And the reason I say this is, so first of all, because the trees interact with the flow through the pressure field, the trees can alter the hill-induced pressure fluctuations in ways that shifts the pressure field and makes the flow appear more, makes the hill appear more steep than it otherwise was. That the canopy, so in the absence of a canopy, that the inertia of the flow and the downward transport of momentum on the lee side of the hills counters the gradient. And if these two terms dominate, that the flow will stay attached and travel down the hill. But if the pressure gradient gets large, that's when flow separation occurs. In the presence of trees, because of the pressure drag, the flow inertia is much lower, and the transport of momentum down by turbulence is lower into the canopy because of the pressure drag handling the momentum sink, that you can get flow separation on the lee of hills at about half the steepness of that which you would otherwise expect. So it's a really serious effect. So I took an LES run. I put trees on the hill. I ran a case. I took those same trees, put it on a flat hill, on a flat terrain, estimated a Z0, and put that same Z0 on the same hill with the same forcing, same everything. And you can show, so this flow separates directly. This flow does not, it separates ever so slightly on the lee side in this particular case, but the point is distinctly different flows just because we're resolving the pressure influence on the flow as opposed to imposing it with a roughness length. So our final, so the key achievements was recognition that turbulence in the RSL is distinct from that in the inertial sublayer, that organized motions dominate that exchange, and that the idea that the canopy operates like a mixing layer with some alterations in that, adds this additional length scale into the problem. That was these are sort of my three key, what I think are the three key achievements. And that the major remaining challenges is really extending buoyancy and the coupling of the canopy and its influence on our theories, because current theory is limited to near neutral flow, and that heterogeneity is still a big problem, as we've discussed all week, and that canopy orography interactions really need a focus. Now, remember, there's a paradigm there where in the orography case that it's really the canopy height relative to the tree height, the canopy height relative to the hill height or the hill length. There's a whole sort of canopy density piece of that there's a phase space where this influence of orography is important, but that on really large hills like you see outside, I think the hills dominate much more than do the trees, but the influence is still there. Okay, thanks.